record to this computer. So here we are. As you can see, here we are starting with our problem set number 5, and we're actually dealing with what is a really exciting week, I think, because it is considered the workhorse of statistics, and that is called simple linear regression. So the goal for today's section is, in about the next 30 minutes or so, we're going to open a data set in RStudio, and we're going to analyze that data set using the tool of simple linear regression. And in fact, we're actually going to take on the role of a type of social scientist called a criminologist. A criminologist is a social scientist who is interested in crime. This is of particular note to me because this is a area of research that interests me personally. Criminology comes from the word crime, of course. And what we're looking at is we're going to look at a data set that is called violence.r data. But what we're going to do is we're going to look at the association between particular country characteristics or their attributes and then their homicide rates or their average homicide rates per 100,000 people. So what we're going to do is quite similar to correlation, but is quite distinct in many respects too. But given that in today's section we're going to focus primarily on the R code, my goal is to get you up to speed with running R code quickly and rapidly into your RStudio environment, uploading those data, analyzing them and inspecting them, and then using some of the functions within Mosaic within the Mosaic package, using those functions to both visualize the association between one quantitative predictor and a quantitative outcome, and as well as look at those associations in terms of the simple linear regression framework. Now, this is more, I think, more focused on the R code because the R code is necessary for understanding the concepts within, I would say, within a coding environment. So while on the one hand you're not mandated to learn R, it is of course very important to learn, but on top of that, it's more important for you to understand and interpret the RStudio output. That is, whatever we see within, if I can annotate, I'm just going to provide a little spotlight here. Whatever is presented here in the console, you should see a little highlight here. If you look at this console here, we'll see some output printed here, and then we'll see some output printed in the plots pane, which is in the lower right-hand corner in my Macintosh working operating system. And the goal is really not just to learn the R code, because at this point it should be pretty rote. It should be pretty routine for you to understand and to manipulate. But it is more importantly to understand and interpret the R output as it is presented to you raw, as you would when you're, say, working with statisticians or interpreting the output produced by statisticians. Because that is going to be much more important than it is knowing the nitty-gritty for the code. That being said, of course, we are emphasizing the code today because I want you to be able to run the code accurately and to successfully complete this portion of the problem set, because this is of course, a considerable part of the homework. So, as usual, within the RStudio environment, of course, we have in the upper right-hand corner, you have what is the R script, what is known as the R code, R scripts, and you can see even what is called the relative path file here, which basically says on my Macintosh computer, you can see that I have the R code within my desktop. See, I'll let it hover. You can see that little floating relative path file. You can see that this is labeled pset5rcode.r. Now, of course, you can rename your script whatever you want. I tend to keep my R code the same name. And of course, I tend to keep my R code the same name as the kind of project that I'm working on, because the benefit of doing statistics in R is that you get to do different kinds of parallel analyses. So here you can see the .r code, which is essentially your recipe. It tells us what it is we want the computer to do. And then we have where we're going to do it, which is our global environment. This basically says to R where it is that we're working. Well, if you notice here in my global environment, you'll look at my files, you'll see that I actually have 2 files located within my desktop. So if you look at my home and you look at my desktop, I've created a file here called pset5. Now you can name that whatever you want. If you look at my desktop, you'll see some other projects here. But typically I try to keep my project encapsulated within a particular folder. So each homework assignment, I encourage you to have, within your homework assignment, I encourage you to have a data set, the relative code, and then you might see something like an R data file or an R history file that is sort of innocuous or invisible. Don't concern yourself with those. In fact, those are just typically created when we open up R, and I think we can delete those. But what you should see within your relative path file, and I encourage you to, again, to go, say, put on your desktop, create a folder called pset5, then place within that folder the data sets for your this week's homework assignments, and then the R code. Now, the R data set, of course, is the type of data frame that we read into R, and R will recognize it immediately. Now, as you can tell, the R code is already open. Now, you can open this actually by clicking on these. If you go to Files and you go to R location, I think you can open these up. If you actually just double click on this, it'll ask me, do you want to load the R data file into the global environment? This is the first way to open a file. You can just click on that. But you'll see within my console, RStudio is pretty helpful because it's telling us already, okay, well, you can do this. You can actually double click on our file name here. But you can also, it's reminding us that we can actually use the code right here and upload the data file this way. I encourage you to copy and paste whatever R code you have that is printed and save that in your R script file, because this is kind of, as I said before, it's like your recipe. It's a reminder to R what it is you're doing. And if you can see, I actually commented out this load command here because you can just repeat this. This is the benefit of writing a script. I'm going to do Command S to save this script because it is read now. But if I save it and I just click at the end of this line where the cursor is, and then I do Command or Control Enter or Return, then I can just load the data set again. Now this is useful because then I can also remove the data frame. Now, to remove a data frame, you can just actually type remove, and I can remove violence.rdata, and it should remove it. Looks like it isn't, though. Hold on for a second. Let's see why. I think it's because it is not recognizing that particular data frame name. I may have to give the whole path file. Looks like I have to give the whole path file. So I can remove the object if I go like this. Or we can just simply the easiest way I would encourage you to do is just actually click the little R button here. Sorry, the little broom button here. This means to remove the objects from the environment, means to unload or detach a data frame. I also can click right here to remove a data frame. Now the point here is I'm just trying to show to you that you can actually use the command interface or the console to load a data frame, as well as you can use the drop-down menus. Additionally, you can use the little buttons here. It doesn't really matter how you do it as long as you just load your data into R. That's all that we care about. The most important thing, though, I would recommend is to have your .R script and your R data file in the same location on your desktop. I cannot emphasize this more than enough. Those of you who are computer programmers will say, Nathan, this is redundant, we already know this, but I would just say to you, for the rest of you, this is what we call data hygiene. This is a huge part for getting replicable code. By replicable code, I just simply mean if we do the analysis once, then we want to be able to do it again, because we're not going to remember what we did 6 months ago. You know, if you can see, this data frame was actually originally created in 2016. We won't necessarily remember what happened September 10th, 2016, and we won't remember the code. You'll see that it was open today, of course, but when we write the code, we won't necessarily remember what it is. So we want to make sure that what we did in the past, we can redo. And that's why I always recommend for you to save your .r file. And when you use when you load files within your relative path file, make sure that you save those commands. Now I'm going to just go straight to the questions here. We're going to use a couple functions here to inspect our data frame once we load it into R. But I just want us to get to this location here. This is what I cannot emphasize more than enough. I'm going to do Control L as a keyboard shortcut to clear out my console. I like to have a nice clean console here. But the point is you should have a data frame here, and it'll be called data, and I have 8 observations with 19 variables. That means we have 18 rows here with 19 variables. Now this is technically what we call a high dimensional data set because we have more variables than we do have observations. This also means that we might want to inspect our data set a little bit because, you know, in the sense that we have lots of variables, we only have 8 observations, we want to know more about these data. Well, what we know from the question and what we know from the homework prompt is that our outcome of interest is actually the murder rate per 100,000 people. So our observation is not at the individual level now, it's at the country level. We're looking at 8 different countries, and we're comparing the murder rate between those 2 different countries and looking at what country level attributes predict country level murder rates. Now, of course, that is important to emphasize because attributes at the country level are distinct from predictors or attributes at the individual level. We cannot say anything about individuals. We're just talking about country aggregates or country level predictors. And it's important to distinguish because not everyone from the country is the same. Just because a country has a high murder rate doesn't mean that the murder rate is necessarily prevalent or even that common. It's still quite rare, in fact. But the point of the matter is that here we have a data set with 8 observations and that we want to, 8 observations and 19 variables. And we want to get a quick handle on that. So we want to know how many observational units are on the data set. When we say observational units, you can look here and you can look in the upper right-hand corner of the environment pane. And you can see that the quickest way perhaps to understand what is in your data frame is to just click once here. And I just clicked that once. I did a single click within my Mac operating system. And you can see that I got a new window up in my upper right-hand corner. And that's just like a typical viewer that you'd see in an Excel worksheet. And it is also a command, the view command. Now, we've seen this before in previous weeks. It's a capital V, so keep in mind, remember that R is case sensitive. So what we did is we viewed the violence data set, and we have a couple, attributes about a few variables about each country that we might want to look at. But let's take a look at these countries we're looking at. We're looking at Australia, Belgium, Guatemala, Jamaica, the Dominican Republic, South Africa, Ukraine, and the United States. So first off, we can get an idea that we're not looking at a representative sample of countries here. This is only 8 countries sampled in 1 year. That is, 8 out of 300 or so countries recognized by the UN. So just to get an idea, we're actually comparing apples and oranges here. We're comparing a very particular subset of all countries within the world. And that's important because whenever we're doing a data analysis, first thing you want to get a hold of is what are we looking at? And so we're getting a look at first the observations here. So we can say, well, when we look at the view function, we can see that there are 8 countries we're comparing. And then it asks, what is the average murder rate per 100,000 across all countries? Well, we can use the mean function here, and that's pretty straightforward. And we can see that the average murder rate is about 22 per 100,000. I also encourage you, I'm going to add this to the work here. I'm going to encourage you to do the favstats function. And you can see that the autocomplete in my working environment was already getting me there. And I'm going to do control return. And you can see that we still get the mean, but we get the mean within context. So we have our sample size here, which is an n of 8. We have not only the mean, but we also have our mean within context. We can see that even when we compare the maximum to the minimum value for murder rates per 100,000, we're only really looking at most 59 per 100,000. That's a very low percentage of the population that is actually affected by murder rates. It is still a huge discrepancy between countries. That's certainly true, right? A minimum of 0.55 means a murder of 1 homicide per 200,000, as opposed to 59 per 100,000, or about 120 per 200,000. That's quite a big disparity. Nevertheless, the key point is that when we're looking at country level attributes, the average does not necessarily tell us about the prevalence. But this is going to be our main outcome of interest for today's homework assignment. It's going to be understanding what predicts variation between these 8 countries in their murder rate. And we can see that this is an adequate variable to study because there is enough variation within the data set. That being said, the caveats that I presented earlier, namely that we're looking at a subset of all countries and that we're looking at country level attributes, those caveats still matter. I encourage you to use the view command to look at the other variables within the data sets, many of which we are not looking at today, but which may be of interest for, say, another homework assignment. What we're looking at, though, is this variable right here. And you can see already, if we're looking at this variable, I'm going to see if I can, if you notice, I actually click on that variable, I can order it from highest to lowest value or lowest to highest value. You can see that the countries differ in their murder rates, with Jamaica being highest, then followed by Guatemala and South Africa. And the lowest is Austria in this sample. Again, the caveats I said still apply, and that's very important because the computer will do whatever analysis you want, but your goal for this class is to be a savvy consumer of statistics. Your goal is to be able to interpret the outcome. So, just as we do with correlation, with simple linear regression, we're interested in the association between two, or in fact with simple linear regression, we can look at 2 or more quantitative variables. But in this case, we're actually just looking at the association between 2 quantitative variables. And the biggest question people ask me almost all the time is, Nate, what is the difference between correlation and simple linear regression? And I would say, fundamentally, you could say there's not much, because in the simple sense, you're still looking at the association between one variable and another. In this case, we might want to use the XY plot to look at the association between life expectancy, or how much you live on average within the country, and its murder rate within the country. And what we're doing is we're just inspecting the association between 2 variables. Then the million-dollar question is, well, what is the difference between simple linear regression and correlation? What I want to emphasize is that simple linear regression focuses on what we call estimation or prediction. That is, we're going to look at the murder rate, but we're going to look at what predicts murder rates. And here our emphasis is on what predictor or various predictors in the x-axis, this is what I'm highlighting right now, are associated with the y-axis outcome, in this case, the murder rates. Now, with the correlation analysis, there's no direction in prediction. We could say the murder rate is hypothesized to predict life expectancy and vice versa. What we're doing when we talk about simple linear regression is we're actually going to analyze predictors, and we're going to look at what the outcome would be given a particular value of our x variable. I kind of liken simple linear regression to our week on conditional probability, or on relative risk, in the sense that we're conditioning our outcome variable, what we often call our expected mean, based on our level of our predictor. So our graphical representation of the variables are going to be the same, but our differences are going to be when we interpret the output. And we're always going to interpret the output in terms of what predicts the outcome, and what would the outcome be at a certain level of the predictor variable. Let me see if I can get us a little bit closer here, because I want us to get more familiar or more comfortable with the idea that we can actually look at the association between 2 variables, first visually. So if we look at the scatter plot in the percent rural, this is a question number 2, or I think there's a different question here. I'm going to actually do an XY plot of these 2 variables, because this is one of the questions in the homework assignment. create a scatter plot between the percentage of people living in a rural area, the rural variable, and the murder rate. What is the relationship? What might explain this relationship? Let's take a look at this output and interpret it. What I want to show to you is, if we look at this output, and I just highlighted the code for question number 2. I know it's not that question number 2 within a homework assignment, but it is number 2 within the kind of tasks that we have in the code. If you look at that question, you can see the output here. And this is crucial, because this is where context matters. We already know that our observations, these little dots here, these are country levels attributes. That means each country here is plotted as the coordinates on a 2-dimensional plane as a function of both the murder rate for each country as well as the rurality, what we're going to call the rurality. That's the percentage or proportion of rural people within that country. So here we look at this country. I already know it's Austria because it has a low murder rate of 0.55, right? We can look at this again. Here's this 0.55 country, and here's Austria. So here we know this country is Austria. And we know that each dot here is a country. So we have 1, 2, 3, 4, 5, 6, 7, 8. We have 8 dots here representing the 8 countries, each of which is represented in the XY plot or the scatter plot as a function of both the X variable and the predictor variable. Now, I want to show you something. We can actually swap out these variables. We can do not just rurality, but we did other variables. Let's do population. And let's get rid of this type here because we don't want to do proportion. And I'll just type this in here. We can look at other variables here. You can see that there's a population variable, and it can represent, again, the murder rate per 100,000 as a function of the population. And it looks like here we're talking about I'd assume in millions. Yep, this looks like it's in millions, so it's a little bit out of date because the US population is about 330 million, and Austria is given a population of about 8 million, but I think those are a little bit low. But the point is, we can just swap out some of these variables and we can look at the association between any quantitative variable, two numeric variables, and look at their association. And we can also look at outliers here. So this country has a very large land area and a relatively low murder rates. I'm going to guess that it's probably the United States. Yep. It looks like if we look at the outliers for land area, it'll be the United States because it is the largest country here. But we might want to look at other things. So let's go back to our variable of interest. We're going to look at rurality. I'm just pressing the up arrow. I think it's a different button on a PC, but I'm pressing the up arrow to go through my commands that I've typed already. And we're going to go back to our code here. And I just ran, sorry, I didn't mean to do that. I'm just going to rerun this code. And just to remind us how to interpret this output, I gave you quite a bit of a sort of disquisition on what each data point means. But now I want to talk about what is the association, what is this, what might explain this association. First, this association we could say is positive because as rurality increases, so does the murder rate. But it is also roughly linear, we might want to say, but not 100% approximated by the linear line, because it looks like in some ways, if we were to draw a straight line here, it might not explain the shape. In fact, if I could draw a line here, I might kind of do something more like a hockey stick. I know that's not a very good approximation, but that's how I draw an association than I would if I were just to draw it by approximating a linear association. And that's an important distinction because what we're doing with simple linear regression is we're going to try to approximate associations in terms of their linear association. So we're going to say this is roughly linear, but not 100% linear. And it's positive. That means that a positive association simply means that the slope here, the rise over the run of the regression line, increases. So as our x variable increases, so does our y variable. I'm going to actually clear the output here, clear all the drawings, and I'm going to actually see if we can find, see if we can actually talk about the regression in terms of, Excellent, press the button here. I want to look at our output, see if we can find a negative association, just so you can see that. Murder rate and GDP, I believe, are negatively associated. So gross domestic product is a measure of economic productivity. So you can see that when we talk about the linear association of the assumptions of the linear model, you can see that it's not always approximated by the data at hand, but it's always important to visualize it. So what I did here was I just plotted the murder rate as a function of GDP. And you can see that there are a few countries that have relatively high GDP and low murder rates. And then you have some countries with low GDP, but which vary dramatically in terms of their murder rates. You have one country down here that has a low murder rate and low GDP. And then you have a country here that has relatively low GDP and a high murder rate. So again, when we talk about the linear assumption, the XY plot is going to be, linearity is not going to, we could draw a line here and assume that we have a linear association, but it doesn't necessarily describe all the data because we have a huge sort of a lacuna here in our data sets between the low GDP countries and the high GDP countries. So the point here is simply, when we talk about correlation and simple linear regression, we want to make sure that we look at our data first. So we can do that through the view function and some other functions. We can also do it through the XY plot function. And we want to understand what the association is. The second question here, I kind of buried a little bit, but let's comment this out. I'm going to do Shift Command C, and I'll type a Control S. And that simply is, what I did was I actually put a little hash mark in front of some text so I can uncomment it. And you can see that it's read in as a command, but we want to actually put a hashtag in front of everything. And we can do that with several lines just to make it a comment. So that way we can annotate our code without ever having to tell our computer to run that code. And I separated this question here in number 2 because it is it's an important one. What might explain the association between murder rate and rurality? Let's take a look at this variable right here. This association, rather. The point I want to make is basically this is where your mind comes in terms of interpretation. Here I kind of drew a line of what I used to indicate a positive linear, roughly linear association between rurality and murder rates between these 8 countries. Now, what might explain this association? We could say, well, given that there's a linear association, a positive linear association, we might want to make some hypotheses here. And this is where generating hypotheses from the data can be useful and informative. But we have to be careful as long as we're simply not fishing for important or surprising results, but that we're actually investigating something of interest. So what might explain rurality and murder rates? I could come up with many questions and many answers here, and I encourage you to think of what you might think. But I would say as a criminologist, you might want to say rurality might actually, say, contribute to murder rates because, well, one hypothesis could be that you have more people who are unemployed. So rurality is a proxy indicator for unemployment rates because, we live in a world that is increasingly globalized and that increasingly relies on technological innovation. And in rural countries with greater rural populations, they may not have as much employment rates, or they may not have as much economic prosperity. Notice what I did here, though, is I'm hypothesizing based on the data. That doesn't mean that we can actually definitively claim any causal association. We can actually simply say, we have a prediction, rurality predicts murder rates, and that in and of itself is important, it's relevant, because knowing something about the country's rurality will tell us something about its murder rate. Just as if you're going to work and interpret statistics for your employer, you might need to interpret, say, what predicts crime rates within your community. Sometimes we're not even interested in what the predictor is. If it's a good predictor, that's good enough, right? This is where proxy variables can fit in. But oftentimes, we're also thinking as investigators, and we want to understand what are the underlying mechanisms. Well, if the underlying mechanism here is unemployment, we might want to look at that. So I had us look at GDP, for example, and it seemed like GDP might not be a good proxy for unemployment, but you might want to look at some other predictors and see if those help to explain the association. But the main point is that we're not changing our mode of analysis when we talk about simple linear regression. We're simply changing our mode of interpretation. We're no longer simply concerned with the association between two variables. We're concerned about what is the outcome, our estimated outcome, given a certain level of our predictor variable. And that's a huge distinction. I know it may not seem, dramatic here, but it's a huge one that distinguishes correlation and simple linear regression. And in fact, it underlies most of the code logic that we have here. We have what we call an XY plot, not because we're just in the association that is non-directional, but precisely because we're interested in what happens when we have a certain level of an X variable. What happens to the Y variable? We're interested in that linear association. And we're interested in understanding it. And even when we have an association, that by itself does not show causation, nor can it really tell us the directionality. Our directionality of our directional hypothesis, namely that rurality is predictive of murder rates, assumes that rurality is an important predictor of an outcome, and that the outcome itself does not predict rurality. So in other words, it's a mode of interpretation where we're interested in understanding what is the value of an outcome given our predictors. Let's take a look at the simple linear model. We have about 20 minutes left. I want to just use in the last few minutes interpreting the coefficients of a simple linear model. And what we do within the R environment is we're going to use this LM function. And we're going to look at rurality, and we're going to predict rurality using a simple linear model. So all we're going to do is we're going to take these two data variables, and we're going to predict murder rates given what we know about rurality within each country. And this is going to be pretty simple. We're just going to run this code here, this model right here, and they're going to print the model, which simply says we're going to show what the results are. And all we did was we asked RStudio to tell us what the coefficients are. And I'm highlighting the coefficients. The coefficients tell us two very important pieces of information. First is the intercept. Second is rurality. Hold on, I have to disable my my screen so we have this same color. The intercept itself tells us the value of the Y variable when X equals 0. Let me repeat that. The intercept tells us the value of the Y variable when X equals 0. So when rurality is equal to 0, what is our hypothesized murder rate? It is negative 13.33. So it's going to be right down here. It's going to be about at the negative point. It's going to be less than 0. And the second piece of information that we get from a linear model is the slope. This is what we often would refer to when I took algebra, we would call it the rise over the run. It is the rise of the linear association over the run, which is the X. So how much does Y increase over the increase of X? So this means that with every 1 unit increase in rurality, the Y variable, the murder rate, increases by 1.13. That means as rurality increases by 1%, the murder rate increases by 1.13 per 100,000. Again, what the slope tells us is what happens to the Y variable as X increases by 1 unit of whatever the X variable is. So again, when we look at the rurality and the murder rate, what we're saying is that the murder rate increases by 1.13 when rurality increases by every 1%. Now notice what these two coefficients have in common. They both interpret what happens to our Y variable as a function of our X variable. This is what distinguishes between linear models and correlations. Correlations can just simply tell us what is the standardized association between two variables. In fact, let's do that right now. We can actually do the correlation between two variables. Let's just do this, just so I can show you. There seems to be a high correlation. A 0.78 correlation between murder rate and virality is relatively high. But what's missing in this correlation? Well, it doesn't tell us what or how to interpret the Y variable or murder rate if we know a particular value of X or virality. And that is the main difference between coefficient or correlation and simple linear models. Simple linear models interpret the Y variable as a function of inputs from the X variable. And correlation is merely a linear association. So if we can talk about the similarities, both the correlation coefficient and the simple linear model both look at the association between two numeric variables. Both look at the linear association between two numeric variables, assuming there's a linear association. Both correlation and coefficient and simple linear models can be examined using the XY plot or the scatter plot function. And that's about it. I'd say linearity. The first fact is that both correlation and simple linear models look at numeric variables, their associations. Both assume a linear association, and both can be plotted using the scatter plots. That's about where our similarities between correlation and linear models stand. Besides that, we're often more interested in the linear model because it'll tell us more about what happens to the Y variable when we have certain values of X. And as I told you, you have more information. We have the intercept and we have virality. We don't have that from the correlation analysis. We only have a simple correlation. We don't know what is the predicted value of murder rates if we had a country that was hypothetically 0% rural. That's out of the data set. And in fact, it doesn't even make sense. So part of the caveat I want to provide is when we look at the simple linear model, the key word is on model. A model is a map of your territory. It is not an exact one-to-one correspondence with what is the reality in your data sets. So sometimes we can have a coefficient that doesn't make any sense given what we know about the data. So I emphasize quite a bit knowing quite a bit about the data because we know that our murder rate cannot be less than 0. You cannot have less than 0 per 100,000 people murdered in a country. So a negative value for Y is not possible. Therefore, our intercept does not make any sense because our intercept is what happens to the Y variable as when X is equal to 0. So that doesn't necessarily matter, except that we want to use some caution when we interpret our linear model because it says to us that there are some bounds on our estimates, that we cannot necessarily blindly estimate our model and then assume that we know everything. We have to look at the data first. In fact, that's why I had sort of a longer disquisition on interpreting and loading the data frame into R. That being said, our slope still makes sense. And in fact, it tells us quite discreetly what happens when you increase the rural proportion within a country by 1%. It increases the murder rate by 1.13 per 100,000. That's a relatively clear, precise interpretation of what otherwise was a quite fuzzy sort of subjective interpretation from question 1. So I know we're only at question 3 here, but I want to emphasize the fact that there are some similarities here as well as some important distinctions from the simple linear model and the correlation. And the main difference is that the simple linear model interprets the linear relationship between two numeric variables in terms of the Y outcome. Now we're going to look at another attribute, which is when we talk about interpreting the Y variable, we're often interested in the proportion of variance explained by our X variable. And this is known as the R-squared. Let me show you what this looks like. I'm just going to run the code for question 4. It's quite high, and it's actually somewhat approximated by the correlation. And it's going to be a little bit misleading here because an R-squared is very similar to a correlation, but we want to distinguish it from a correlation because R-squared is bound by 0 and 1, but it is always positive. So unlike a correlation, an R-squared tells us what proportion of variance in the Y outcome, again, the murder rate, is explained by the X variable. It does not tell us the association between two variables. So R-squared is a little bit different. It's about, I would say it's one of the third most important pieces of information after the slope and the intercept. We often want to know what the R-squared is. This is the proportion of variance explained in our X variable, given what we know in our Y variable. Sorry, this is the proportion of variance explained by our Y variable, given what we know with our X variable. Here we have an X variable, an R-squared of 0.6, which tells us that about 60%, or in fact 61%, rounding, 61% of the variance in our murder rate is explained by rurality. That is a high R-squared. An R-squared, again, is the proportion of variance in our Y variable explained by our X variable. Notice that there's some distinctions here. When we talk about R-squared, we're saying the proportion in variance explained. We're saying, given that we know that the murder rate varies, because this is the first thing that I emphasize in today's section, we see the variance here from 59 to 0.55. There's some variation here. And if we look at the favstats function, we can see that the standard deviation is 22. So it varies quite a bit. Our average is about equal to the standard deviation. That means we have quite a bit of variance in our outcome. And we can see that in our scatter plot. So given that our Y variable varies, how much of that variance in that Y variable is predicted by rurality? And we can roughly say 60%. We can assign our how much of the variance that we can explain with an actual number. And this proportion is always positive. So the main distinction, as I said before, is the difference between correlation and R-squared is that correlation can be negative and positive and show directionality, but the R-squared is always positive. So if you want to see directionality, you look at the slope, in fact. A positive slope indicates a positive association. A negative slope indicates a negative indication. And that's what the second coefficient indicates here. So I think we're going to wrap up today, but I wanted to emphasize, even though we've gone through only question 4, we'll go through the rest later in tomorrow's section. But I want to emphasize these 4 main points, which is essentially the differences. First of all, I'd say loading data into R, and then interpreting and understanding R output. Linear regression vis-a-vis correlation. And this is where we look at both the console and the plots panes. Then we talk about understanding the data and the context of the analysis. This is crucial. We spend most of our time getting up to this point, and then in particular, we finally focus on 3 aspects of simple linear regression. We talked about the intercept, the slope, and R-squared. Those are 3 crucial, important differences. But then, on the other hand, I showed us that we have so many similarities. So for tomorrow, we're actually going to look at a little bit more on prediction. And when I talk about prediction, I'm actually talking about what is the value of Y for a particular value of X. And this is different than the slope. So if I want to say, okay, given that a country has, say, a rural proportion of 45%, what is our estimated or predicted value of y, given that we would estimate our virality to be about 45%. That's what we're going to focus on for tomorrow. That being said, you should be able to run all of this code so far, and you should be able to interpret all the outputs and all the questions given what I provided so far. But I want to end the section just on those 3 points, or on those 4 points. And we'll just, to leave you with focusing on the rest of the questions, maybe looking more at prediction if you would like, but at least they give you the bits and pieces of simple linear regression that are crucial, that are imperative for completing the homework for this week. Thank you very much, everyone. And if you have any particular questions, feel free to ask them. Otherwise, I'll see you tomorrow.